Chapter 5.1 and 5.2, Work and Power. Chapter 5 and the rest of the semester test plan is as follows. On Monday, Tuesday, Wednesday, and Thursday, we will cover chapters 5.1 and 5.2. On Monday and Tuesday, we'll cover 5.1 predominantly and do some practice problems. Wednesday and Thursday, there will be a quiz covering chapter 5.1 and 5.2, and we'll work on some practice problems for 5.2. Winter break starts on the 20th and is over on January 4th, 2015. On that Monday, January 5th and 6th, we will cover chapter 5.3 and take a quiz and then work on some practice problems. On the 7th and 8th of January, we'll cover chapter 5.4 with a quiz and do some practice problems. On the 9th and 12th, we'll review chapter 5. On the 13th and 14th, we'll review the semester. On the 15th and 16th, we'll take the semester test. The semester test will be made up of a number of different things. Since there will be no chapter 5 unit test, it will make up about 25% of the semester test. These will need doing problems, so it is very important that you go over chapter 5 to make sure you understand how to do those problems. Chapters 1, 2, 3, and 4 will make up the rest of the semester test. Roughly 3/4 or 75% of the test questions for the semester test will come directly from the chapter 1, 2, 3, and 4 unit tests. The rest will be new questions. Make sure you have all 4 unit tests so you can start reviewing now. And you will be able to have a note card sheet for the test. The learning targets for chapter 5.1 or work are as follows. I can recognize the difference between the scientific and everyday definition of work. I can define and explain work by relating it to force and displacement. I can calculate and describe the net force when many forces are applied to an object. The learning targets for chapter 5.2 or energy are as follows. I can identify several forms of energy. I can explain and calculate kinetic energy for an object. I can distinguish and describe kinetic energy and potential energy. I can distinguish and describe different types of potential energy, and I can calculate gravitational potential energy. Lesson outline, short notes on work on Monday and Tuesday, classwork practice 5A and section summary. Homework is to read chapter 5, section 1 and 2. Make sure you watch the screencast on Sophia and take the practice quiz. You will be quizzed on it next period for both sections 1 and 2. Work depends on the amount of force applied to an object, the distance the object moves while the force is applied, and the direction of the force with respect to the direction the object moves. The product of force and the amount of displacement along the line of action of that force gives you the equation work is equal to force times displacement. Common units are feet-pounds, or horsepower, Newton-meter, or joule. Work is equal to force times distance. To calculate work done on an object, we need the force, the average magnitude of the force and the direction of the force, the displacement, the magnitude of the change of position, and the direction of the change of position. Positive work is performed when the direction of the force and the direction of the motion are the same. If you can see from the drawing, the direction of the force is from left to right on an object. The direction of the movement as a result of the force is also from left to right. This is considered positive work. Formula work is equal to force times x. Negative work is performed when the direction of the force and the direction of motion are not in the same direction. From this drawing, you can see that the wind-up toy car is being pulled back even though it is going in a forward direction. The direction of the force is opposite direction the object moves. Work is equal to minus force times x. When the kinetic energy of an object changes, work has been done on that object. It is considered a scalar quantity. The units are 1 kilogram meter squared over second squared, or a joule. Force is not work. If the force is perpendicular to the direction the object moves, the work done is 0. If the object doesn't move, the work done is 0. Energy is defined as the capacity to do work. Many forms exist. None are created, only converted. Examples are chemical, sound, heat, nuclear, and mechanical energy. Two other ones that are important for this unit are kinetic energy, or the energy of motion, and potential energy, or the energy due to position or deformation. Kinetic energy is a scalar quantity. Common units of kinetic energy are 1 kilogram meter squared over second squared, or joule. If an object is moving, it has energy. Be careful that the opposite statement of this is not always true. This energy is called kinetic energy, or the energy of motion. Energy to motion reflects the mass and the velocity of an object, and the equation is kinetic energy is 1/2 mass times velocity squared. Calculating kinetic energy. How much kinetic energy is in a 5-ounce baseball thrown at 80 miles per hour? Your givens are the mass is given as 145 grams, which you then convert to kilograms, and giving you 0.15 kilograms. The velocity, 80 miles per hour, is converted to meters per second, or 35.8 meters per second. Your unknown is kinetic energy. You use the formula 1/2 mv squared, plugging in the numbers, and you end up with 92.9 Newton meters, or 92.9 joules. Potential energy. Sometimes work is not converted directly into kinetic energy. Instead, it is stored or hidden. Potential energy is stored energy or stored work. This person on top of the hill has a ball. The ball is not rolling down anywhere. It has potential energy. Once it's pushed over, it will convert into kinetic energy. There are two forms of potential energy. Gravitational potential energy is the energy due to an object's position relative to the Earth. Elastic potential energy is due to the deformation of an object. Elastic potential energy is affected by the object's amount of deformation. Greater deformation means you have greater potential energy that's elastic. Delta x squared is the change in length or deformation of an object from its undeformed position. Stiffness is the resistance of being deformed. The variable is K, which is equal to stiffness or spring constant of material. Potential energy of its elastic is 1/2 K delta x squared. Gravitational potential energy of an object at height h is equal to the negative of the work that gravity does when an object is lifted from the potential energy equals 0 position. You will notice this swing or pendulum has 3 different heights and various potential energies. The energies on the outside are larger because the height is higher. Calculating potential energy, this is sample problem 5D on page 179 of your textbook. Your givens are mass is 70 kilograms, K 71.8 Newton meters over meters, gravity is 9.8 meters per second squared, the height is 50 meters minus 44 meters, which is equal to 6 meters, x is 44 minus 15 meters, or 29 meters, and potential energy is 0 joules at river level. What you're looking for is the potential energy total, which is equal to the potential energy due to gravity and the elastic potential energy. Calculating potential energy due to gravity is mass times gravity times height. Plugging in the numbers, you end up with 4.1 times 10 to the third joules. Elastic potential energy is 1/2 kx squared, or 1/2 71.8 Newton meters over meters times 29 meters squared. Gives you 3.02 times 10 to the 4 joules. Potential energy total is 4.1 times 10 to the 3rd joules plus 3.02 times 10 to the 4th joules, or 3.43 times 10 to the 4th joules. This is an illustration of how you can convert from kinetic energy to gravitational potential energy, and then gravitational potential energy to kinetic energy, and finally kinetic energy back to gravitational potential energy, and so forth. Read Chapter 5, Section 1 and 2. Watch a screencast on Sophia and take the practice quiz. You will be quizzed on both next period for both Sections 1 and 2.